LangChain Astra DB Store Summary. None. Detailed definition of the variable goes here. Components. Component 1. A Python class that enables storing and retrieving data from data stacks Astra DB. A cloud-native database service. Using LangChain. Component 2. This class facilitates the integration of LangChain with Astra DB, enabling users to leverage Astra DB as a persistent storage mechanism for their language models and applications. Description of the architecture supporting the variable. Astra DB, a fully managed, serverless, and scalable database ASA service, is built on Apache Cassandra. It offers high availability, low latency, and global data distribution, making it an ideal choice for applications demanding reliable and performant data storage. Explanation of the variable's role in the system. The Astra DB Store class acts as a bridge between LangChain and Astra DB. It handles the interactions with Astra DB, enabling efficient and structured storage and retrieval of data. This empowers users to build sophisticated and potent applications that leverage the capabilities of both LangChain and Astra DB. Simplified integration with Astra DB enables seamless connection between LangChain and Astra DB for data storage and retrieval. Efficient data management provides optimized methods for managing data storage and retrieval within Astra DB. Scalability and reliability leverages Astra DB's inherent scalability, high availability, and reliability, ensuring seamless operation and robust data handling. Limited features may lack advanced features compared to other storage options, potentially restricting functionality in specific scenarios. Dependency on Astra DB requires a running Astra DB instance for functionality, making it reliant on the availability of this database service. Advantage 1. Chroma offers a user-friendly interface, simplifying the integration of embedding-based retrieval into applications. This means that developers can easily use Chroma to add embedding-based retrieval capabilities to their applications, without having to write a lot of code. For example, a developer could use Chroma to add a search feature to a website or application, without having to write a lot of code for the search functionality. Advantage 2. Chroma's efficient indexing and searching capabilities provide fast and accurate retrieval results. This means that Chroma can be used to perform similarity search on large datasets, without sacrificing speed or accuracy. For example, a search engine could use Chroma to find documents that are similar to a given query, and the results would be returned quickly and accurately. Challenges. Challenge 1. Chroma, as a vector database, relies on embedding models for effective similarity search. This means that the performance of Chroma is dependent on the quality of the embedding models that are used. If the embedding models are not accurate, then the results of the similarity search will not be accurate either. Challenge 2. Managing and updating embeddings in large datasets require efficient data management strategies. This means that Chroma needs to be able to efficiently store and update the embeddings that are used for similarity search. If the embeddings are not managed efficiently, then the performance of Chroma can be degraded. LangchainCohere chat models get Cohere chat request. A detailed description of how to generate a Cohere chat request using LangChain constructs a dictionary containing the necessary components for a Cohere chat request. Component 1. The name of the Cohere model to use for generating responses. For example, Command X large nightly or Command 4x4 nightly are Cohere models suitable for chat applications. Controls the randomness of the generated responses. Higher values closer to 1 result in more creative and unpredictable responses. The maximum number of tokens the model should generate in a response. A token is a basic unit of text, roughly equivalent to a word. Influences the selection of the next token during generation. It limits the selection to the top k most likely tokens. Controls the probability distribution of the next token. It considers the probability of the top p most likely tokens. Specifies sequences of tokens that should stop the model's generation. This can be used to prevent the model from generating responses that are too long or that go off topic. The user's input that the model will use to generate a response. This is the text that the user types into the chat interface. Provides context and instructions for the model. This can be used to guide the model's responses in a specific direction. Utilizes LangChain's chat models to interact with the Cohere application programming interface and generate responses. LangChain's chat models provide a convenient way to interact with Cohere's chat models, allowing you to send requests and receive responses without needing to directly handle the API. Details. Facilitates the creation of chat requests for Cohere models, enabling conversational interactions with the models using LangChain. It makes the process of building a chat application with Cohere simpler by providing a standardized way to construct requests and receive responses. Simplifies the process of interacting with Cohere models by abstracting away the complexities of dealing with the Cohere application programming interface directly. Provides a structured and standardized approach to crafting requests, making it easier to build consistent and reliable chat applications. Ensuring compatibility with the Cohere application programming interface requirements. Cohere's API has specific formatting and data types for requests, and ensuring compliance with these requirements is essential for successful communication. Optimizing request parameters for desired response quality and efficiency. Parameters such as temperature, max tokens, and top k influence the model's behavior. Finding the right balance between creativity, length, and performance is crucial. The getRole method relies on the LangChain framework, which provides a robust infrastructure for managing and interacting with various large language models (LLMs), including Cohere models. This framework facilitates seamless communication with the Cohere API and handles the retrieval of role information from the Cohere service. Role. The getRole method acts as a query mechanism for accessing and retrieving the role associated with a specific Cohere chat model. This role provides valuable insight into the intended purpose and capabilities of the model, informing its selection for different tasks. Advantages. Understanding the model's role empowers users to select the most appropriate model for their specific needs, maximizing the model's effectiveness and ensuring it aligns with the intended purpose. By providing information about a model's capabilities and limitations, the getRole method aids users in making informed decisions about model selection, ensuring the chosen model is suitable for the task at hand. For example, a model designed for text summarization may not be suitable for creative writing. Understanding the model's role helps users avoid using it inappropriately. Challenges. While providing useful information about the model's intended purpose, the role description might not encompass the full range of capabilities of the model. This could lead to misinterpretations of the model's potential and limitations, resulting in unintended consequences. The model's role may evolve over time as it is updated and refined, potentially leading to discrepancies between the retrieved role information and the actual capabilities of the model. Regular updates of the role description are crucial to maintain accuracy and ensure the information remains relevant. For instance, a model initially designed for simple text generation might be enhanced to support code generation. In later versions, this evolution requires updating the model's role description to reflect its expanded capabilities. LangChainCohere Agent explained. A detailed description. LangChainCohere Agent is a powerful tool that combines LangChain, a framework for building applications using large language models (LLMs), and Cohere, a company that provides an application programming interface API for accessing these LLMs. It allows applications to interact with the real world through the capabilities of LLMs. Component 1. LangChain is a powerful framework for building applications that utilize large language models (LLMs). It provides a modular and flexible way to connect LLMs to different data sources and other applications. LangChain allows developers to build complex applications that leverage the power of LLMs for tasks such as text generation, translation, summarization, and question answering. Component 2. Cohere is a company that provides an application programming interface API for accessing large language models (LLMs). The API allows developers to easily integrate LLMs into their applications. Cohere also provides a suite of tools and resources to help developers build and deploy LLM-powered applications. The LangChainCohere agent is a LangChain agent that utilizes a Cohere large language model (LLM) as its core component. This architecture combines the flexibility and modularity of LangChain with the power and capabilities of Cohere's LLMs, allowing for a wide range of applications. The LangChainCohere agent serves as an interface between LangChain and Cohere. It acts as a bridge, allowing LangChain to leverage the capabilities of Cohere's LLMs. This role is crucial for enabling LangChain applications to utilize the power of LLMs provided by Cohere. The LangChainCohere agent can be used to build a wide variety of applications that interact with the world. Some examples include chatbots, which can engage in natural language conversations with users; question answering systems, which can provide answers to user queries based on a knowledge base; and text summarizers, which can condense large amounts of text into concise summaries. The LangChainCohere agent is designed for ease of use. Developers can quickly and easily integrate it into their applications. The agent is also highly customizable, allowing developers to tailor it to meet the specific needs of their applications. The capabilities of the Cohere LLM used by the agent may limit the agent's functionality. For example, the LLM might not be able to perform certain tasks or might not be able to perform them with a desired level of accuracy. The LangChainCohere agent might not be as efficient as a native LangChain agent. This is because the agent needs to communicate with the Cohere API, which can introduce latency and overhead. Components. None. Component 1. LangChain, a framework for building applications powered by language models. LangChain offers a modular and flexible approach to integrating large language models (LLMs) into various applications. It provides tools and libraries for tasks like data retrieval, processing, and interaction with LLMs. For instance, you can use LangChain to build a chatbot that retrieves information from a database and then uses an LLM to generate a response based on that information. Component 2. Cohere Chat Models. Language models designed for conversational interactions. Cohere chat models are specifically tailored for engaging in natural, human-like conversations. They are trained on vast amounts of text data and are capable of understanding and responding to prompts in a conversational manner. These models can be used for various conversational applications, such as chatbots, virtual assistants, and conversational AI systems. Component 3. Get role function provides access to the predefined persona or role of the chat model. This function allows developers to retrieve the specific role or persona assigned to a Cohere chat model. This role defines the model's intended behavior and conversational style. For example, a chat model designed for providing customer support might have a role of helpful and informative, while a model for creative writing might have a role of imaginative and expressive. Provides clarity about the model's intended purpose. By retrieving the assigned role, developers gain a clear understanding of how the model is intended to be used and the type of interactions it is optimized for. This helps developers make informed decisions about how to integrate the model into their applications. Enables development of contextually relevant interactions. Knowing the model's role allows developers to design interactions that are appropriate and meaningful. For example, if a model is designed to be a humorous chatbot, developers can craft prompts that elicit humorous responses. Limited functionality only retrieves the assigned role. This function is limited in its scope and only provides information about the model's predefined persona. It does not offer additional functionalities, such as customization or modification of the assigned role. Dependence on predefined roles relies on the existing persona of the model. The getRole function depends on the predefined role assigned to the model by the developer. It does not allow for dynamic or user-defined roles. This can be a limitation if developers need to create models with more nuanced or customizable personas. Challenge 2. Description of Challenge 2. Optimizing the request dictionary to maximize the quality and relevance of responses from Cohere. LangChainCohere agent. Definition. Detailed definition of the variable goes here. Components. Component 1. This function helps understand how chat models can be utilized in different settings. For example, a chat model might be used for customer service interactions, providing information, or creating content. Understanding the model's intended role helps users to choose the right model for the task at hand. Component 2. It helps users to understand the intended use cases of the model, such as conversation, question answering, or creative writing. For example, a model designed for conversation might be less effective for creative writing tasks. By understanding the model's role, users can avoid using it for tasks it is not designed for. Architecture. Description of the architecture supporting the variable role. Explanation of the variable's role in the system. LangChain's getRole function helps users grasp the intended application of a chat model within a given context. It acts as a guide to understand the model's capabilities and limitations. For instance, a chat model designed for question answering might not be effective for generating creative text. The function helps users understand these limitations and make informed decisions about how to use the model. Advantages. Better understanding of the model's intended application. For example, understanding a model's role as a question answering tool allows users to ask it appropriate questions and expect relevant answers. Facilitates appropriate model selection for specific tasks. If a user needs to write a blog post, they can select a model designed for creative writing rather than a model designed for customer service. Challenges. Model roles might not be fully defined or accurate in some cases. Some models may have a broad range of capabilities, making it challenging to define their role precisely. For example, a model designed for creative writing may also be capable of answering questions or providing customer service. Dynamic nature of chat models may lead to role evolution over time. As chat models improve, their capabilities may expand, leading to changes in their roles over time. For example, a model designed for question answering may become capable of generating creative content in the future. This evolution requires users to constantly reassess the model's role and adapt their expectations. Langchaincohere Common Cohere Citation. Noun. A class that provides functionality for citing cohere models within LangChain applications. This class ensures that when you use cohere models in your LangChain projects, you can properly attribute the model source. It allows for transparent and responsible use of the models. Component 1. The cohere citation class itself, which is the core of this functionality, acting as a centralized point for all interactions related to citing cohere models. Component 2. A cohere model, like the command summarize models from cohere, that you would use within your LangChain application. The cohere citation class relies on the cohere application programming interface API to gather information about the cohere model being used. It leverages the API's capabilities to retrieve details like model name, version, and training data, crucial for proper citation. The cohere citation class provides a standardized and consistent approach to citing cohere models. This ensures that all instances of citing cohere models within LangChain projects follow a predefined format, promoting uniformity and easing understanding of model attribution. Using the cohere citation class promotes transparency by clearly indicating which cohere models are used within a LangChain project. This allows users to understand the origin and characteristics of the models employed, fostering trust and accountability in the usage of these models. By providing a defined mechanism for citing models, the cohere citation class enables easier reproducibility of the results achieved using these models. This becomes essential when sharing or replicating projects that rely on these models, as others can easily understand and replicate the setup. As Cohere updates its application programming interface API over time, the Cohere citation class may require adjustments to maintain compatibility with the latest API functionalities. This could involve updating the class code to interact seamlessly with the new API version, ensuring continued proper functioning. The current version of the Cohere citation class focuses primarily on citing cohere models. It may lack comprehensive support for models from other providers, potentially limiting its applicability in scenarios involving models from various sources. Offers insights into model capabilities. Access to role information through the getRole function provides valuable insights into capabilities of cohere models. These roles often reflect the model's training data, intended applications, and specific expertise. Understanding these roles helps users assess the model's suitability for their tasks, ensuring they are appropriately leveraging the model's strengths. This informed approach maximizes the value of the model's output and enhances the overall effectiveness of its application. Limited role information availability for some models. In some cases, the Cohere API may not provide comprehensive role information for specific models. This limitation might occur due to various factors, such as the model's age, its training data, or the API's current design. In such instances, the getRole function may return incomplete or limited role information, requiring users to rely on other sources for a complete understanding of the model's capabilities. Potential for API rate limiting issues. The use of the Cohere application programming interface API to retrieve role information can be Subject to rate-limiting mechanisms, these mechanisms are implemented to manage server resources and prevent abuse. If the get-role function exceeds the API's usage limits, it may encounter delays or be blocked, potentially disrupting the retrieval of role information. Developers should be mindful of the API's rate limits and implement appropriate strategies to avoid exceeding them, ensuring uninterrupted access to model information. LangChain-cohere LLM integration. Summary and key attributes and a description of the key attributes. LangChain-cohere LLM integration combines the strengths of Cohere's powerful large language models LLMs with the flexibility and ease of use of the LangChain framework. This combination empowers developers to build and deploy applications that leverage the capabilities of advanced AI models, such as text generation, summarization, and translation, without the need for extensive in-house AI expertise. Component 1. LangChain is an open-source framework that streamlines the process of building and deploying applications powered by large language models (LLMs). It provides a modular architecture that allows developers to easily integrate and utilize different LLMs, including Cohere's models. LangChain offers pre-built components and tools for common LLM tasks, such as text generation, question answering, and summarization, which significantly reduce the development time and effort. Component 2. Cohere is a leading provider of advanced large language models (LLMs) that excel in various natural language processing tasks. These models are trained on massive datasets and exhibit exceptional capabilities in text generation, summarization, translation, and more. Cohere's LLMs are accessible through a user-friendly application programming interface (API), allowing developers to seamlessly integrate them into their applications. Real-world applications of Cohere's LLMs include generating creative content, summarizing lengthy documents, translating text between languages, and providing interactive chatbot experiences. LangChain's modular architecture allows for seamless integration of Cohere's LLMs within applications. This approach facilitates the connection and utilization of Cohere's models in a flexible and scalable manner. Developers can easily incorporate Cohere's LLMs into their workflows, leveraging the powerful capabilities of these models without needing to manage complex infrastructure or build custom integrations. LangChain-cohere LLM integration empowers developers to unlock the full potential of Cohere's LLMs through the user-friendly and adaptable LangChain framework. This integration provides a convenient and efficient way to access and utilize the advanced capabilities of Cohere's models within various applications. Developers can leverage the features of LangChain, such as pre-built components and streamlined workflows, to quickly and effectively build LLM-powered applications that enhance user experiences and drive business outcomes. The LangChain-cohere LLM integration offers access to Cohere's powerful large language models, enabling developers to leverage the advanced capabilities of these models in their applications. Cohere's LLMs are known for their exceptional performance in tasks such as text generation, summarization, translation, and question answering, providing developers with a wide range of tools to enhance their applications. The integration provides a simplified way to connect and utilize Cohere's LLMs through LangChain's modular architecture. This modular approach allows developers to easily integrate Cohere's models into their applications, without needing to write complex custom code or manage extensive infrastructure. LangChain's pre-built components and tools further streamline the integration process, reducing development time and effort. Utilizing Cohere's LLMs can result in significant costs due to their advanced capabilities and processing power required to operate them. Developers need to carefully consider their budget and usage patterns to ensure that integration is cost-effective. Exploring alternative cost optimization strategies, such as using Cohere's models for specific tasks rather than for all operations, can help mitigate these costs. Managing the security of application programming interface API keys and access control is crucial. When working with Cohere's LLMs, developers need to implement robust security measures to protect their API keys and prevent unauthorized access to their Cohere accounts. This involves implementing secure authentication methods, restricting access to authorized users, and regularly reviewing security practices. Summary of langchaincohere LLMs base Cohere. NaN. LangChain's base Cohere class is a wrapper around the Cohere application programming interface, providing a standardized interface for using Cohere models. It simplifies interactions with Cohere's text generation and understanding capabilities within LangChain framework. For example, a user could use base Cohere to generate different creative text formats like poems, code, scripts, musical pieces, email, letters, etc., or to understand and summarize text, translate languages, and write different kinds of creative content. Component 1. Cohere Application Programming Interface Client handles communication with the Cohere application programming interface, including sending requests and retrieving responses. For example, this component handles the sending of requests to Cohere for generating different creative text formats like poems, code, scripts, musical pieces, email, letters, etc., or to understand and summarize text, translate languages, and write different kinds of creative content. It then retrieves the responses from Cohere and returns them to the LangChain framework. Component 2. LangChain's large language model interface adheres to the large language model interface, ensuring compatibility with other LangChain components, such as chains and agents. For example, this component allows the user to use base Cohere with other LangChain components to build complex language processing pipelines. The base Cohere class acts as a bridge between Cohere's application programming interface and LangChain's framework, enabling seamless integration of Cohere models into LangChain applications. For example, this allows the user to use Cohere models to generate different creative text formats like poems, code, scripts, musical pieces, email, letters, etc., or to understand and summarize text, translate languages, and write different kinds of creative content. Within a LangChain application, base Cohere serves as a convenient wrapper for using Cohere models within LangChain, simplifying the process of accessing and utilizing Cohere's capabilities. For example, a user could easily access and use Cohere models to generate different creative text formats like poems, code, scripts, musical pieces, email, letters, etc., or to understand and summarize text, translate languages, and write different kinds of creative content. Within a LangChain application, simplified access to Cohere models provides a user-friendly interface for interacting with Cohere's services. For example, a user could use base Cohere to easily access and use Cohere models to generate different creative text formats like poems, code, scripts, musical pieces, email, letters, etc., or to understand and summarize text, translate languages, and write different kinds of creative content. Interoperability with LangChain components enables integration with other LangChain components for building complex language processing pipelines. For example, the user could combine base cohere with other LangChain components to build complex language processing pipelines. Limited control over Cohere application programming interface parameters may not offer fine-grained control over all Cohere application programming interface parameters. For example, the user may not be able to specify all the parameters that are available in the Cohere application programming interface. Potentially less efficient than direct application programming interface calls, the wrapper may introduce some overhead compared to direct application programming interface calls. For example, the user may experience a slight performance degradation when using base Cohere compared to directly calling the Cohere application programming interface. LangChaincohere LLMs. Summarized information for Cohere in LangChain as a detailed description of each aspect. LangChaincohere LLMs. Cohere is a large language model LLM offered by Cohere Inc., which specializes in generating text, translating languages, and writing different kinds of creative content. LangChain makes it possible to utilize Cohere within your applications through its integration, granting you access to Cohere's capabilities. Components. Component 1. Cohere's application programming interface. This refers to the set of rules and specifications that allow your application to interact with the Cohere LLM. You can send requests to the API to perform tasks like generating text, translating languages, or writing different kinds of creative content. Component 2. LangChain integration. LangChain is a framework that simplifies the use of LLMs like Cohere. It provides a consistent way to interact with Cohere's API, abstracting away the complexities of making API calls and handling responses. The architecture of LangChaincohere LLMs involves using Cohere's application programming interface within a LangChain framework. This framework allows you to effectively utilize Cohere's abilities for tasks like text generation, translation, and content creation. The role of LangChaincohere LLMs is to simplify and streamline the integration of Cohere's powerful language capabilities within your projects and applications. Easy integration. Integrating Cohere into your applications is straightforward with LangChain, as it provides a well-defined interface for interacting with Cohere's API. Powerful language abilities. Cohere's LLM excels at various language-related tasks, including text generation, translation, summarization, and creative content creation. Potential for cost. Using Cohere's API can incur costs, depending on your usage volume. Application programming interface. Rate limits. Cohere's API may have rate limits, meaning you can only make a certain number of requests within a specific time period. LangChaincohere LLM SA completion with retry. Definition. A specialized LangChain wrapper that leverages Cohere's text completion capabilities and incorporates a retry mechanism for increased robustness. It attempts to generate text by submitting requests to the Cohere application programming interface, handling potential errors and retrying until a successful response is received. This component ensures reliable text generation even in the presence of network hiccups or temporary API issues. Components. Component 1. LangChain is a powerful framework that simplifies interaction with various language models and tools, enabling the creation of complex natural language processing applications. Imagine a chatbot that can access external databases, summarize documents, or translate languages. LangChain provides the building blocks for such functionalities. Component 2. Cohere is a sophisticated and versatile language model that excels at a range of natural language processing tasks such as text generation, translation, and summarization. Imagine generating creative content, translating documents between languages, or condensing lengthy articles into concise summaries. Cohere is a versatile tool for these tasks. Component 3. The retry mechanism is a crucial component that enhances the robustness of the text generation process. It acts as a safeguard against temporary errors, ensuring the completion process continues despite transient issues like network glitches or AP fluctuations. Imagine a scenario where you are generating a long piece of text and encounter a temporary network interruption. The retry mechanism ensures that the text generation process continues without requiring manual intervention. Architecture. The architecture involves a LangChain wrapper that seamlessly interfaces with the Cohere application programming interface to handle text completion requests. In case of errors, the retry mechanism kicks in, diligently attempting to resend the request multiple times. If all attempts fail to resolve the issue, an exception is raised, informing the user of the persistent error. Role. This component acts as a vital bridge between the LangChain framework and the powerful Cohere model. It provides a user-friendly interface for accessing Cohere's capabilities while offering a reliable retry mechanism to mitigate network disruptions or transient errors. Imagine a user wanting to leverage Cohere's text generation abilities without worrying about network issues or temporary AP hiccups. This component simplifies the process, ensuring a smooth and reliable experience. Advantages. Enhanced robustness. Retries help handle temporary issues, increasing the likelihood of successful text generation. This leads to a more reliable and consistent text generation experience, even in the face of minor network interruptions or AP fluctuations. Improved reliability. The retry mechanism helps ensure the task's completion even if temporary errors occur. This ensures that the text generation process continues uninterrupted, minimizing disruptions and maximizing productivity. Challenges. Handling persistent errors. If the underlying Cohere application programming interface encounters a persistent issue, retries might not be effective. Imagine a scenario where the Cohere AP is experiencing a major outage. In such cases, retries might not resolve the issue, and the text generation process might fail. Network interruptions. In case of network failures, retries might be insufficient to overcome the interruption. If a network outage persists, retries might not be sufficient to reconnect and resume the text generation process. The component utilizes LangChain's application programming interface for interacting with Cohere's language models, while also implementing retry logic to handle scenarios where the application programming interface call might fail. This architecture ensures that the text generation process remains reliable even in the presence of intermittent network issues or temporary service disruptions. Role. This component facilitates reliable text generation by ensuring that application programming interface calls to Cohere's language model are attempted multiple times in case of initial failures. The completion with retry component acts as a safeguard, ensuring that the text generation process is not interrupted by temporary hiccups in communication with Cohere's language model. Advantages. Enhanced reliability ensures text generation despite intermittent application programming interface issues. By retrying failed application programming interface calls, the completion with retry component ensures that the text generation process is not interrupted by temporary glitches in the communication with Cohere's language model, thus increasing the overall reliability of the system. Improved user experience provides a more consistent and reliable interaction. The A completion with retry component contributes to a smoother user experience by masking potential issues related to the application programming interface communication with Cohere's language model. This results in a more consistent and reliable interaction, as users are less likely to encounter errors or interruptions in the text generation process. Challenges. Application programming interface rate limits. Cohere might impose limits on the number of requests per time period. To avoid exceeding these limits, the A completion with retry component should incorporate mechanisms to manage the frequency of application programming interface calls. For example, it could implement the back-off strategy, where the delay between retry attempts increases with each consecutive failure. Or it could use a token bucket algorithm to regulate the rate of application programming interface calls. Application programming interface failures, transient network issues, or Cohere service disruptions could cause failures, while the A completion with retry component addresses these issues by implementing retry logic. It's important to note that persistent failures might require further investigation and resolution. The component should be equipped to handle situations where retrying the application programming interface calls does not resolve the issue, such as by logging the failures or notifying the application developers for manual intervention. Langchain chroma vector stores cosine similarity. Definition. Detailed definition of the variable goes here. Components. Component 1. Langchain's chroma vector stores are a powerful way to store and search vectors in a database. Chroma uses FAISS Facebook AI similarity search for fast approximate nearest neighbor search, making it efficient for large datasets. Chroma allows users to store and retrieve vectors efficiently while leveraging FAISS's speed and accuracy. Component 2. Cosine similarity is a metric used to measure the similarity between two vectors. It ranges from 1 to 1. Where 1 indicates a perfect match and 1 indicates perfect opposition. A value close to 0 means that the vectors are orthogonal and have no correlation. It's a common similarity metric used in various applications, including text analysis, image recognition, and recommender systems. Consider two sentences like the cat sat on the mat and the cat was sitting on a mat. Their corresponding vectors might be slightly different, but the cosine similarity will be closer to 1, indicating a high degree of similarity between these sentences. Architecture. Description of the architecture supporting the variable. The chroma vector store is implemented using FAISS. It stores vectors in a compressed format for efficient storage and fast retrieval. When performing a similarity search, the cosine similarity is calculated between the query vector and the vectors in the database. FAISS, being a library for efficient similarity search, is instrumental in Chroma's architecture. It enables rapid retrieval of similar vectors from the database, making it well suited for large datasets. Role. Explanation of the variable's role in the system. Cosine similarity plays a crucial role in Langchain's chroma vector stores. It enables the system to measure the similarity between text embeddings and retrieve relevant documents based on semantic meaning. When users input a query, Langchain converts it into a vector representation. Using cosine similarity, Chroma then searches for the vectors in the database that are most similar to the query vector, allowing users to retrieve relevant information. Advantages. Advantage 1. Efficient vector storage and retrieval through FAISS. Chroma leverages FAISS to store and retrieve vectors efficiently, enabling rapid search and retrieval of similar vectors. especially in large datasets. FAISS's efficient algorithms for approximate nearest neighbor search ensure quick and efficient retrieval of relevant vectors. Advantage 2. Accurate similarity measurement using cosine similarity. Cosine similarity provides a robust way to measure the similarity between vectors, enabling Chroma to accurately retrieve vectors that are semantically close to the query. This is particularly important in applications like document search, where the semantic meaning of the query is crucial for retrieving relevant documents. Challenges. Challenge 1. FAISS is approximate, potentially leading to slight inaccuracies in nearest neighbor search. While FAISS excels in efficiency, its approximate nature can lead to slight inaccuracies in the retrieved results. FAISS may sometimes return vectors that are slightly less similar to the query compared to an exact search, especially in cases where the vectors are very close in similarity. Challenge 2. Chroma's performance may be impacted by large dataset sizes. While Chroma is optimized for handling large datasets, its performance can be impacted by the sheer size of the data. Large datasets might require more computational resources and time to process. Increasing the size of the dataset might lead to increased time for indexing, searching, and retrieving vectors. Langchaincohere arg retriever. This YAML document outlines the definition, architecture, role, advantages, and challenges associated with utilizing langchaincohere arg retriever for retrieval augmented generation. Langchaincohere arg retriever is a powerful tool that combines the strengths of Cohere's large language model with LangChain's retrieval capabilities. Components. Component 1. LangChain. This library provides a comprehensive framework for building and deploying large language model-based applications. LangChain simplifies the process of integrating LLMs into various applications, making it easier to leverage their power. Component 2. Cohere. A powerful language model known for its strong performance on various tasks. Cohere is a cloud-based service offering advanced language models with capabilities like text generation, summarization, translation, and question answering. Component 3. RAG retrieval augmented generation, a technique for improving large language model performance by retrieving relevant information from a knowledge base. RAG enhances the quality of outputs by providing LLMs with context-specific information from a curated source. Architecture. The architecture of LangChaincohere RAG retriever leverages the following key components. 1. Document loader responsible for loading the knowledge base into a format that can be processed by the retriever. 2. Retriever searches the knowledge base to find relevant documents based on user queries. 3. Embedder encodes both queries and documents into numerical vectors to enable efficient similarity search. 4. Cohere LLM utilizes the language model's capabilities for generating text based on the retrieved documents. Role. LangChaincohere RAG retriever plays a crucial role in enabling accurate and contextually relevant text generation. It combines the strength of LLMs with the ability to access and retrieve relevant information from a knowledge base. This approach enhances the quality of generated text by providing the LLM with contextual information. Advantages. Improved accuracy and relevance. Retrieval augmented generation ensures that the large language model has access to relevant information. By grounding responses in a relevant knowledge base, RAG can help LLMs produce more accurate and contextually appropriate outputs. For instance, when asked about a specific event, The LLM can consult a database of historical records to provide a factual and accurate response. Enhanced contextuality. The retrieved information provides the large language model with a deeper understanding of the topic. With access to relevant documents, the LLM can gain a more comprehensive grasp of the topic, leading to more nuanced and informative responses. For example, if the LLM is asked to write a summary about a particular scientific topic, it can consult research papers and articles on the subject to gather more context and produce a more accurate and detailed summary. Faster and more efficient RAG significantly reduces the need to fine-tune LLMs for specific tasks. RAG eliminates the need to fine-tune LLMs for specific tasks, making it a more efficient approach. For example, instead of fine-tuning the LLM for answering questions about a specific domain like healthcare, RAG can leverage a knowledge base of medical articles and information to provide accurate responses to user queries. Challenges. Limited knowledge base. The effectiveness of RAG depends heavily on the quality and comprehensiveness of the knowledge base. The performance of RAG hinges on the accuracy and completeness of the underlying knowledge base. If the knowledge base is incomplete or contains inaccurate information, it can negatively affect the quality of generated text. For example, if the knowledge base lacks information about a recent event, the LLM might generate responses based on outdated or inaccurate data. Retrieval limitations. The ability to retrieve relevant documents is crucial for RAG's success. The success of RAG hinges on the ability of the retriever to accurately identify and retrieve relevant documents from the knowledge base. If the retriever fails to identify relevant documents, the LLM will not have access to the necessary information to produce a high-quality response. For example, if a user asks a question about a specific product feature, the retriever needs to accurately identify the relevant product documentation to provide the LLM with the necessary information. Integration complexity. Combining different components like retrievers, embedders, and LLMs can be challenging. Combining various components like retrievers, embedders, and LLMs necessitates careful integration and configuration to ensure seamless operation. This can be a complex process requiring expertise in different areas like information retrieval, machine learning, and natural language processing. For example, ensuring compatibility between different retrieval algorithms, embedding models, and LLM architectures can be challenging and require careful optimization. Challenge 1. Ensuring the knowledge base is comprehensive and accurate is crucial for successful retrieval. This requires careful curation and maintenance of the knowledge base. Steps involved in maintaining the knowledge base. Step 1. Regularly update the knowledge base with new information. This step involves continuously adding new information to the knowledge base to keep it up to date. It's crucial to include recent developments, news articles, research papers, and other relevant data to ensure the knowledge base is current. For instance, a medical knowledge base needs regular updates with new research findings and medical breakthroughs. Step 2. Validate the accuracy of existing data and remove outdated information. It's essential to regularly validate the accuracy of the existing information in the knowledge base. Outdated or inaccurate information should be removed or corrected to prevent the LLM from generating misleading responses. This process can involve fact-checking, cross-referencing with reliable sources, and expert review. Step 3. Ensure the knowledge base is structured in a way that is easily searchable. The knowledge base should be structured in a manner that enables efficient retrieval of relevant documents. This can involve using appropriate data structures, implementing efficient indexing methods, and adopting a suitable search engine. For example, a knowledge base containing legal documents might be structured using hierarchical categories, keywords, and search tags to enable easy retrieval of relevant legal information. Challenge 2. The efficiency and effectiveness of retrieval play a critical role in RAG. The retriever must accurately identify relevant documents based on user queries. Steps involved in optimizing retrieval. Step 1. Select a retriever that is appropriate for the knowledge base. Structure and query types. The choice of retriever depends on the structure of the knowledge base and the types of queries it will be handling. For instance, if the knowledge base is organized as a database of structured data, a database-specific retriever might be more suitable. For unstructured text data, a document-based retriever might be more appropriate. Step 2. Fine-tune the retriever's parameters to improve its accuracy. Fine-tuning the retriever's parameters can enhance its accuracy and retrieval effectiveness. This involves adjusting parameters like similarity thresholds, ranking functions, and query weighing to improve the precision and recall of the retrieved documents. For example, by adjusting the similarity threshold, you can control the number of documents retrieved, ensuring only the most relevant documents are included. Step 3. Experiment with different embedding models to enhance the similarity search process. Different embedding models can encode queries and documents into numerical vectors with varying degrees of accuracy and efficiency. Experimenting with different embedding models can significantly improve the similarity search process and lead to more relevant retrievals. For example, some embedding models might be better at capturing semantic relationships between words, leading to improved results for queries involving synonyms or related concepts. Challenge 3. Combining different components requires careful integration and configuration to ensure seamless operation. This involves setting up the connections between the retriever, embedder, and LLM. Steps involved in integrating the components. Step 1. Choose compatible components that work well together. Selecting compatible components is crucial for seamless integration. This involves ensuring that the retriever, embedder, and LLM are compatible in terms of input and output formats, data structures, and API interfaces. For example, the retriever should be able to output data in a format that can be processed by the embedder, and the embedder's output should be compatible with the LLM's input requirements. Step 2. Configure the components to work with the specified knowledge base and query format. The components need to be configured to work with the specific knowledge base and query format. This includes specifying the knowledge base location, data format, and the expected query format. For example, you might need to configure the retriever to access a specific database. Configure the embedder to work with a specific type of text data, and configure the LLM to handle a specific query format. Step 3. Test the integrated system to ensure that it produces the expected results. Thorough testing is crucial to ensure that the integrated system functions as expected. This involves testing the system with various types of queries, validating the accuracy of responses, and evaluating the overall performance of the system. For instance, you can test the system with a range of queries, including simple and complex questions, and verify that the retrieved documents and the LLM's responses are accurate and relevant. Langchaincohere RAG retrievers. Cohere RAG retriever. Description of Cohere RAG retriever. Cohere RAG retriever is a retriever class that uses Cohere's RAG application programming interface to Retrieve relevant documents from a corpus based on a given query. Description of components. Description of Component 1. Cohere's RAG Application Programming Interface. It leverages Cohere's RAG Application Programming Interface to retrieve documents. Description of Component 2. RAG Retrieval Augmented Generation. Cohere's RAG Application Programming Interface is based on a RAG technique. Description of Architecture. Cohere RAG Retriever uses a combination of Cohere's RAG Application Programming Interface and a vector database to facilitate the retrieval process. Description of Role. It is a retriever class designed for retrieving documents from a corpus using Cohere's RAG Application Programming Interface. Description of Advantages. Description of Advantage 1. Leverages Cohere's advanced RAG capabilities for effective document retrieval. Description of Advantage 2. Integrates seamlessly with LangChain for building retrieval-based applications. Description of Challenges. Description of Challenge 1. Requires access to Cohere Application Programming Interface and appropriate credentials for usage. Description of Challenge 2. May face performance limitations depending on the size of the corpus and query complexity. Increased reliability. The retry mechanism significantly enhances the reliability of the text generation process by handling temporary errors and network issues. This ensures that text generation tasks are completed successfully even in the presence of unforeseen circumstances. Advantage 2. Error resilience. This variable incorporates a retry mechanism that makes the text generation process more resilient to errors. If the LLM encounter an error, the retry mechanism will attempt to re-execute the request, providing a robust solution for handling unexpected issues. Challenge 1. Handling network issues. This variable effectively addresses errors that may occur during interaction with the LLM, such as timeouts, invalid responses, or application programming interface API rate limiting. The retry mechanism helps mitigate potential network issues, such as temporary outages or connection problems, by retrying the request after a specified delay. Challenge 2. Mitigating errors in LLM responses. The retry mechanism helps mitigate potential network issues, such as temporary outages or connection problems, by retrying the request after a specified delay. For example, if there is a temporary network glitch or an API rate limit is reached, the retry mechanism will wait for a specified time and then reattempt the request, ensuring the text generation process continues smoothly. Challenge 3. Ensuring consistent text generation by implementing retries. It ensures that the text generation process remains robust and consistent, even in the presence of unforeseen issues. This ensures that users receive a consistent and reliable text generation experience, regardless of potential issues. LangchainCohere React Multi-Hop. A description of LangChain's multi-hop reasoning capability using Cohere, encompassing definition, components, architecture, role, advantages, and challenges. A combination of LangChain's chain and Cohere's large language model LLM designed to perform multi-hop reasoning. This approach leverages the strengths of both frameworks to enable complex question answering and problem solving that require multiple steps of reasoning. Component 1. LangChain, a framework for building applications powered by language models. LangChain provides a powerful and flexible interface for building applications that use large language models LLMs such as Cohere. It allows for the creation of complex pipelines that combine different LLMs and other components, making it easy to build applications for natural language processing tasks. LangChain offers a wide range of features for creating and managing chains of language models, including prompting, Data retrieval and result processing. Component 2. Cohere, a powerful large language model (LLM) known for its reasoning capabilities. Cohere is a state-of-the-art LLM developed by Cohere.ai. Known for its ability to perform complex reasoning tasks and generate human-quality text. It is particularly well suited for tasks that require multi-step reasoning, such as question answering, summarization, and text generation. The architecture involves a multi-hop reasoning chain in LangChain. This chain is built by connecting multiple modules that perform different reasoning steps. Each module can be an LLM, a retrieval component, or a processing step. These modules are interconnected in a chain to form a complex reasoning process. To enable complex question answering by combining LLMs and reasoning capabilities. LangChain's multi-hop reasoning chain, powered by Cohere, enables the answering of questions that require multiple steps of reasoning. Imagine a question like, what is the capital of the country where the Eiffel Tower is located? This question requires reasoning steps. First, identify the country where the Eiffel Tower is located, France, and then find the capital of France, Paris. Improved accuracy in multi-hop question answering. By combining the capabilities of LLMs and reasoning chains, this approach can improve the accuracy of question answering systems, especially for complex questions that require multiple reasoning steps. Enhanced reasoning abilities for complex tasks. The combination of LangChain and Cohere allows for the creation of applications capable of performing more complex tasks involving multi-step reasoning. This can be applied to areas like text summarization, knowledge extraction, and dialogue systems, enhancing the efficiency and effectiveness of these applications. Handling long chains of reasoning can be computationally expensive. As the number of reasoning steps increases, the computational complexity of the process grows. This can pose challenges for resource-constrained applications and might require optimization techniques to ensure efficiency. Maintaining consistency and coherence across multiple hops. With multi-hop reasoning, maintaining consistency and coherence across multiple reasoning steps is crucial. This requires ensuring that each step builds upon the previous ones and contributes to a logical and accurate final outcome. LangChaincohere React Multi-Hop Parsing Cohere Tools React Agent Output Parser. Definition. Detailed definition of the variable goes here. The Cohere Tools React Agent Output Parser is a class in LangChain that parses the output from a Cohere React agent. It is designed to extract the relevant information from the agent's output, such as the final answer, intermediate steps, and any additional information. For example, if a user asks what is the capital of France, the Cohere React agent might provide a series of steps. 1. Identifying France as the country. 2. Looking up the capital of France. 3. Returning the answer Paris. The Cohere Tools React Agent Output Parser would then parse this output and extract the final answer, Paris, along with the intermediate steps. Architecture. Description of the architecture supporting the variable. The parser is designed to work with the Cohere React agent, which is a large language model LLM that can be used for multi-hop reasoning. The agent uses a series of steps to solve a problem, and the parser extracts the information from each step. This allows for a better understanding of the reasoning process and can be used to improve the agent's performance. For example, if the agent makes a mistake, the parser can identify the step where the error occurred, allowing developers to debug and improve the agent. Role. Explanation of the variable S role in the system. The parser plays a crucial role in the LangChain framework by providing a structured way to access the information generated by the Cohere React agent. This enables developers to easily integrate the agent's capabilities into their applications. By providing a consistent and structured way to access the agent's output, the parser simplifies the integration process and allows developers to focus on building their applications rather than dealing with the complexities of the agent's output format. For example, a developer could use the parser to integrate the Cohere React agent into a chatbot, allowing the chatbot to answer complex questions using multi-hop reasoning. Advantages: the parser provides a standardized way to extract information from the agent's output, making it easier to integrate the agent into other applications. This allows for easier integration into other applications, such as chatbots, search engines, or knowledge bases. By providing a consistent and structured way to access the agent's output, the parser simplifies the integration process and allows developers to focus on building their applications rather than dealing with the complexities of the agent's output format. The parser can extract additional information such as intermediate steps, making it possible to understand the reasoning process of the agent. This can be useful for debugging and improving the agent's performance. For example, if the agent makes a mistake, the parser can identify the step where the error occurred, allowing developers to debug and improve the agent. Challenges: the format of the agent's output may change, requiring updates to the parser to ensure compatibility. This is a common challenge with any parser that interacts with a dynamic system. To mitigate this challenge, the parser should be designed to be flexible and adaptable to changes in the agent's output format. This could involve using a standardized format for the agent's output or implementing a mechanism for automatically updating the parser based on changes in the agent's output. The parser needs to be robust enough to handle different types of agent outputs and potential errors or unexpected results. This is important to ensure the parser can handle any unexpected data or errors in the agent's output. For example, the parser should be able to handle situations where the agent's output is incomplete, inconsistent, or contains errors. This could involve implementing error handling mechanisms, using validation techniques to ensure the data is consistent, or using a robust parsing library to handle unexpected data formats. LangchainCohere React Multi-Hop. A comprehensive overview or YAML with elaborations of scalar values. A robust and efficient method for handling multi-hop question answering utilizing Cohere's powerful language model within the LangChain framework. This system enables applications to answer complex questions that require multiple steps of reasoning and data retrieval by combining the strengths of LangChain, Cohere, and React. For example, consider a question like what is the capital of the country where the 2022 FIFA World Cup was held? To answer this, the system would first need to identify the country that hosted the 2022 FIFA World Cup, Qatar, and then retrieve the capital of Qatar, Doha. Component 1. LangChain provides the necessary infrastructure for building and orchestrating the question answering process. This framework facilitates connecting and managing various components such as language models, data sources, and other tools. It acts as the backbone of the system, enabling the seamless integration and execution of different functionalities. Component 2. Cohere leverages its advanced language capabilities to understand context, infer relationships between entities, and generate accurate responses. This powerful language model excels in understanding natural language and generating meaningful responses. It plays a crucial role in comprehending the user's question, extracting relevant information from various data sources, and formulating a coherent answer. Component 3. React enables the creation of an interactive user interface to facilitate user queries. This JavaScript library empowers the development of a user-friendly interface that allows users to easily input their questions and receive responses. By providing an intuitive front-end design, React enhances the overall user experience and makes the question-answering process seamless. The system combines the strengths of langchaincohere and React, forming a comprehensive solution. The combination of these three technologies allows for a robust and efficient multi-hop question answering system. LangChain provides the framework for orchestrating the process. Cohere's powerful language model handles the complex reasoning and information retrieval. And React ensures a user-friendly interface for interacting with the system. To empower applications with the ability to answer complex questions that require multiple steps of reasoning and data retrieval. The aim of the system is to enable applications to handle complex questions by leveraging multiple data sources and reasoning steps. This enables applications to provide more comprehensive and accurate responses to user queries. Enhanced accuracy, coherence, advanced language understanding capabilities lead to more precise answers. The use of Cohere's advanced language understanding capabilities significantly improves the accuracy of the system. Its ability to comprehend context, infer relationships, and process complex information results in more precise and reliable answers. Efficient multi-hop reasoning streamlines the process of navigating multiple data sources to uncover the information needed. By efficiently navigating multiple data sources, the system can retrieve the necessary information to answer multi-hop questions. This streamlined process ensures that relevant data is accessed and processed efficiently, leading to faster and more accurate responses. User-friendly interface. React's intuitive front-end design makes querying and receiving responses a seamless experience. The intuitive user interface, designed using React, provides a seamless and enjoyable experience for users. Users can easily input their questions and receive responses without any technical complexities, making the question answering process simple and efficient. Maintaining context. Ensuring that the language model effectively maintains context across multiple hops to produce coherent responses. One of the key challenges in multi-hop question answering is maintaining context across multiple reasoning steps. The language model must effectively track and utilize contextual information to ensure the coherence and accuracy of the final response. Data source management. Efficiently organizing and accessing relevant data sources to support multi-hop question answering. Managing and accessing relevant data sources is crucial for multi-hop question answering. The system must effectively organize and retrieve data from multiple sources to ensure that the necessary information is available for answering complex questions. Handling complex queries. Developing strategies to handle intricate queries with multiple levels of reasoning. Another challenge lies in handling complex queries that involve multiple levels of reasoning. The system needs to develop strategies to effectively break down these complex queries into manageable steps, allowing it to process and answer them accurately. Summarization of langchaincohere. React multi-hop parsing. Parse answer with prefixes. None. Detailed definition of the variable goes here. Components. Component 1. LangChain is a powerful library for developing applications that leverage the capabilities of large language models (LLMs). It acts as a framework for building complex systems that interact with LLMs and integrate them into various workflows. LangChain simplifies the process of working with LLMs by providing tools and components for tasks like data retrieval, question answering, summarization, and more. Real-world applications of LangChain include chatbot development, document analysis, and content creation. Component 2. Cohere is a prominent provider of large language models, offering access to advanced AI models through an application programming interface API. Cohere's models are trained on massive datasets of text and code, enabling them to perform a wide range of natural language processing tasks, including text generation, translation, summarization, and question answering. Their API provides developers with a simple and efficient way to integrate these models into their own applications. For example, a developer could use Cohere's API to build a chatbot that can generate realistic and engaging conversation, or a tool for summarizing lengthy articles or documents. Component 3. React multi-hop is a technique for answering questions that require multiple steps to arrive at a solution. Instead of directly answering the question, the approach involves breaking down the question into a series of sub-questions, each addressing a specific aspect of the original query. The answers to these sub-questions are then combined to produce the final answer. This technique is particularly valuable when dealing with complex questions that require reasoning over multiple pieces of information. For instance, a question like what is the capital of the country where the Eiffel Tower is located could be tackled using React multi-hop by first identifying the country where the Eiffel Tower is located, France, and then finding its capital, Paris. Component 4. Parsing is the process of transforming text into a structured format that is easier for computers to understand and process. This involves analyzing the text, identifying its components, and representing them in a structured way, such as a tree or graph. Parsing is essential for various natural language processing tasks, including question answering, machine translation, and sentiment analysis. For example, when answering a question like what is the capital of France, a parser would analyze the sentence, identify the key components, the question word what, the noun capital, and the proper noun France, and represent them in a structured format that can be used by the question answering system. Component 5. Parse answer with prefixes is a function that enhances the process of parsing answers by adding context-aware prefixes to the extracted information. These prefixes provide additional context and help to improve the accuracy and clarity of a parsed answer. For instance, if a question asks for the name of a person and the answer is John Doe, adding a prefix like name before the answer would explicitly identify the extracted information as a name. This helps in disambiguating the answer and ensuring its proper interpretation. Description of the architecture supporting the variable. The architecture leverages LangChain as a framework for building an LLM application that utilizes Cohere's large language model for question answering. The application utilizes React multi-hop to handle complex questions by breaking them down into smaller steps and combining the answers from each step to produce a comprehensive solution. Parsing is used to structure the response, ensuring that the information extracted from the LLM is presented in a clear and understandable format. Parse answer with prefixes further enhances the parsing process by adding context-aware prefixes to the extracted information, improving accuracy and clarity. Explanation of the variable's role in the system. This variable plays a crucial role in providing an effective and efficient mechanism for extracting meaningful information from text by leveraging the power of large language models and advanced parsing techniques. It combines various components, including LangChain for application development, Cohere for providing access to powerful language models, React multi-hop for handling multi-step questions, and parsing for structuring the extracted information. Together, these components contribute to a system that can efficiently process and understand natural language, extract relevant information, and deliver accurate and comprehensive answers. Improved accuracy in multi-hop question answering. By breaking down complex questions into smaller steps, React multi-hop allows the system to address each component individually, leading to more accurate and reliable answers. Enhanced context understanding through parsing. The structured format produced by parsing helps the system understand the context of the extracted information and interpret it correctly. Ability to handle complex and nuanced questions. The combination of powerful language models from Cohere and the ability to process multi-step questions using React multi-hop enables the system to handle complex and nuanced questions that require deeper understanding of the underlying text. Handling ambiguity and uncertainty in multi-hop reasoning. When dealing with multiple steps in question answering, the system may encounter ambiguous or uncertain information. Addressing these challenges requires robust techniques for reasoning and making decisions under uncertainty. Ensuring robust parsing and answer extraction. Parsing text accurately and extracting the correct information from the parsed text is crucial for the overall success of the system. Ensuring the robustness of these processes requires careful selection of parsing algorithms and thorough testing. Optimizing performance for large-scale applications. As the scale of the application grows, it becomes important to optimize the performance of the system to handle large volumes of data and queries efficiently. This may involve optimizing algorithms, using efficient data structures, and utilizing distributed computing architectures. LangchainCohere React Multi-Hop Parsing Cohere Tools React Agent Output Parser Summary. NaN. A specialized class designed to process the output from Cohere tools, utilizing React to parse and manage multi-hop responses. This class provides a structured approach for handling complex responses generated by Cohere tools, which often involve multiple steps or interactions. Component 1. Cohere Tools React Agent Output Parser. This component represents the core parser class that handles the parsing of output received from Cohere tools. It acts as the primary interface for interacting with Cohere tool responses and transforming them into a usable format for the application. Component 2. React-based parsing logic for Cohere tool output. This component refers to the specific parsing logic implemented using React. React is a popular JavaScript library for building user interfaces, and it is employed here to provide a flexible and dynamic framework for parsing the responses from Cohere tools. The React-based approach allows for efficient rendering and updating of the parsed information on the user interface, ensuring a responsive user experience. Leveraging React components to manage parsing of responses from Cohere tool interactions. The overall architecture relies on React components to handle the parsing and processing of responses from Cohere tool interactions. This architectural choice allows for modularity and reusability, as different parts of the parsing logic can be encapsulated within separate React components. This approach also makes the parsing process more maintainable and adaptable to changes in the Cohere tool response structure. Facilitates parsing and extracting information from multi-hop responses generated by Cohere tools. This component plays a crucial role in facilitating the parsing and extraction of information from responses generated by Cohere tools. It acts as an intermediary, transforming raw Cohere tool output into a structured format that is easily understood and processed by the application. This allows the application to effectively utilize the information extracted from multi-hop responses, enabling more complex and dynamic interactions with Cohere tools. Simplified handling of complex responses by using a dedicated parsing class. The handling of complex responses from Cohere tools becomes simplified. The class encapsulates the parsing logic, reducing the complexity of managing diverse response formats and providing a consistent interface for interacting with Cohere tool output. This allows developers to focus on the core application logic rather than dealing with intricate parsing details. Enhanced flexibility and control over response processing. React provides a highly flexible framework for building user interfaces. Using React components for parsing allows for greater control over the response processing logic. This allows developers to tailor the parsing process to specific requirements and easily adapt to potential changes in Cohere tool response formats. This flexibility is essential for handling evolving API responses and ensuring the application remains compatible with future updates. Ensuring efficient and accurate parsing of diverse Cohere tool responses. One of the primary challenges is ensuring efficient and accurate parsing of diverse Cohere tool responses. Cohere tools can generate responses in various formats, depending on the specific tool and the input provided. The parser class needs to be robust enough to handle these diverse formats and extract the relevant information accurately. This involves careful design and implementation of parsing algorithms that can adapt to different response structures and data types. Adapting to potential changes in Cohere tool output formats. Cohere tools, like many APIs, may undergo updates and changes that could affect the format of their responses. The parsing class must be designed to be adaptable to these changes to maintain its functionality and avoid breaking the application. This requires a mechanism to handle potential differences in response structures and ensure that the parsing logic remains compatible with future versions of Cohere tools. LangchainCohere React Multi-Hop Parsing Parse Actions. Description of LangchainCohere React Multi-Hop Parsing Parse Actions. LangchainCohere React Multi-Hop Parsing Parse Actions is a function used within the LangchainCohere React multi-hop parsing system to parse actions from a user prompt. The system is built using LangchainCohere, React, and multi-hop reasoning for question answering. Description of components. Description of Component 1. LangChain is a framework for building and deploying language models. It provides a library of tools and components that can be used to create custom language models for a variety of tasks, such as question answering, summarization, and translation. For instance, LangChain allows you to connect different language models and data sources to create a chain of actions that can be used to answer complex questions. Description of Component 2. Cohere is a language model application programming interface API for generating text, translating languages, writing different kinds of creative content, and answering your questions in an informative way. Cohere offers various pre-trained models that can be used for different tasks, such as text generation, summarization, translation, and question answering. Description of Component 3. React is a JavaScript library for building user interfaces. It provides a component-based architecture that makes it easy to create reusable UI elements. It helps in building interactive and dynamic user interfaces by providing a way to manage the state of the application and to efficiently update the UI when the state changes. Description of Component 4. Multi-hop reasoning is a technique used to answer questions that require multiple steps of inference. It involves using multiple pieces of information to arrive at an answer. For example, to answer the question what is the capital of France, you would need to know that France is a country and that Paris is the capital of France. Description of Component 5. Pass actions is a function that takes a user prompt as input and returns a list of actions that need to be taken to answer the question. This function analyzes the user's prompt to identify the key elements, such as the entities and the relationships between them. It then generates a plan of actions that can be used to answer the question. For instance, if the user asks what is the capital of France, pass actions would identify France as the entity and capital as the relation. It would then generate a plan of actions that would involve retrieving information about France from a knowledge base and extracting the capital city. Description of architecture. The architecture supporting the variable involves the interaction between the following components. User. The user provides a question or prompt. LangChain. The LangChain framework is used to manage the flow of the conversation and to interact with the Cohere language model. Cohere. The Cohere language model is used to understand the user's question and to generate a response. React. The React library is used to build the user interface of the system. Multi-hop reasoning. The multi-hop reasoning technique is used to answer questions that require multiple steps of inference. Description of role. The role of the langchaincohere React multi-hop parsing pass actions is to process the user's prompt and extract the relevant actions needed to answer the question. It analyzes the prompt to identify the key elements, such as the entities and the relationships between them, which are then used to generate a plan of actions. For example, if the user asks what is the capital of France, pass actions would identify France as the entity and capital as the relation. It would then generate a plan of actions that would involve retrieving information about France from a knowledge base and extracting the capital city. Description of advantages. Improves accuracy of the system by providing a structured approach to answering complex questions. By breaking down the question into a series of steps, the system can more accurately identify the information needed to answer the question. Reduces the number of steps required to answer a question by providing a clear plan of actions. A clear plan of actions allows the system to efficiently retrieve the necessary information and to answer the question more quickly. Description of challenges. The function might struggle with complex prompts that require multiple steps of inference. In such cases, the function may need to be able to understand the relationships between multiple pieces of information and to generate a plan of actions that can be used to retrieve the information needed to answer the question. The function needs to be robust enough to handle different types of prompts and to identify the key elements correctly. For instance, it needs to be able to handle prompts that are phrased in different ways, such as what is the capital of France? And where is the capital city of France located? It also needs to be able to correctly identify the key elements in the prompt, such as the entities and the relationships between them. LangChaincohere React multi-hop parsing pass actions. A comprehensive guide to understanding and utilizing this powerful tool. Detailed definition of the variable goes here. Components. Component 1. LangChain, a framework for building powerful language models. LangChain is a Python framework that allows developers to create and deploy applications that use large language models (LLMs). It provides a set of tools and components for working with LLMs, including a variety of pre-trained models, a modular architecture, and a rich set of integrations with other tools and libraries. For example, developers can use LangChain to build applications that generate text, translate languages, write different kinds of creative content, and answer your questions in an informative way. Component 2. Cohere, a cloud-based application programming interface for natural language processing (NLP). Cohere is a cloud-based NLP API that provides developers with access to a variety of pre-trained models for tasks such as text generation, classification, summarization, and question answering. Cohere also offers a variety of features that make it easy to integrate with other applications and services. For example, Cohere's API can be used to build chatbots that can hold conversations with users, or to create applications that can analyze and understand text data. Component 3. React Multi-Hop, a technique for retrieving information from multiple sources. React Multi-Hop is a technique for retrieving information from multiple sources by following a series of steps, or hops, from one source to another. This technique is often used in applications that need to retrieve information from a variety of sources, such as a knowledge graph, a database, or a set of documents. For example, a React multi-hop application could be used to answer a question by first retrieving information from a knowledge graph, then using that information to retrieve relevant documents, and finally using those documents to provide an answer. Component 4. Parsing, the process of analyzing and interpreting data. Parsing is the process of analyzing data, such as text, code, or data structures, and interpreting its meaning. This process involves breaking down the data into smaller units and then using rules to determine the relationships between those units. For example, a parser could be used to analyze a sentence and determine the grammatical structure of the sentence, or to analyze a program and determine how the program is supposed to execute. Component 5. Parse actions, a set of instructions for how to process data. Parse actions are a set of instructions that define how to process data after it has been parsed. These actions can be used to perform a variety of tasks, such as extracting information, transforming data, or generating new data. For example, a parse action could be used to extract the subject and verb from a sentence, or to convert the date from one format to another. Description of the architecture supporting the variable. LangChain provides the foundation for building the application. Cohere application programming interface is integrated into LangChain for NLP tasks. React multi-hop is a technique for retrieving information from multiple sources. Parsing involves analyzing and interpreting the data retrieved. Parse actions define the steps for processing the data. Explanation of the variable's role in the system. LangChaincohere React multi-hop parsing parse actions plays a crucial role in enabling complex information retrieval and processing tasks. It leverages the power of Cohere for NLP, utilizes the multi-hop technique for retrieving information from multiple sources, and applies parsing and parse actions to analyze and process the data. Efficient information retrieval enables retrieval of information from multiple sources effectively. This allows the system to gather comprehensive insights from diverse data sources, enhancing its ability to provide richer and more relevant information. For example, imagine a system that needs to answer a question about a specific event. By using React multi-hop, the system can search for relevant information in a database, a news website, and a social media platform, effectively retrieving the comprehensive and multifaceted understanding of the event. Flexible processing offers flexibility in defining and executing data processing steps. This allows users to customize the system to meet their specific needs. For example, a user could create a parse action that extracts specific information from a text, such as the names of people or organizations, or creates a pass action that converts a date from one format to another. This flexibility allows the system to be used for a wide range of tasks. Enhanced accuracy improves accuracy through the use of NLP techniques. This allows the system to better understand the meaning of the data it processes, resulting in more accurate outputs. For example, a system that uses NLP techniques to analyze text can better understand the nuances of language, such as sarcasm or irony, and can therefore provide more accurate summaries and interpretations of the text. Complexity. Implementing and managing complex multi-hop workflows can be challenging. This requires a deep understanding of the data sources and the relationships between them, as well as the ability to design and implement efficient algorithms for retrieving and processing data. Data consistency. Ensuring consistency across different data sources can be difficult. This requires careful planning and execution to ensure that the data from different sources is properly integrated and that inconsistencies are identified and resolved. Performance. Processing large amounts of data can impact performance. This can be addressed through optimization techniques, such as caching and indexing, to improve the speed and efficiency of data processing. Scalability. Scaling the system to handle large volumes of data and requests can be challenging. This requires careful architecture design and the use of distributed systems and cloud computing to ensure that the system can handle the increasing demands of data and user requests. Langchaincohere LLMs enforce stop tokens. Definition. The langchaincohere LLM's completion with retry function is a strategy that utilizes cohere's large language models (LLMs) to generate text. It ensures successful completion of text generation tasks by implementing a retry mechanism, reattempting the task if initial attempts encounter errors. Components. Component 1. Cohere AI LLM, a large language model developed by Cohere AI. Known for its proficiency in text generation tasks, LLMs are trained on massive datasets, enabling them to understand and generate human-like text. For example, Cohere AI's LLM can be used to generate different creative text formats, like poems, code, scripts, musical pieces, email, letters, etc., or to translate languages, write different kinds of creative content, and answer your questions in an informative way. Component 2. Retry mechanism, a critical error handling technique that automatically reattempts the text generation task if the initial attempt fails. This ensures that the task is eventually completed, even if errors occur. The retry mechanism is a common practice in software development, where transient issues like network interruptions can cause temporary failures. By repeatedly retrying the task, the retry mechanism increases the likelihood of success. Architecture. The langchaincohere LLM's completion with retry function leverages the capabilities of Cohere's LLMs for text generation. If an error occurs during text generation, the retry mechanism is triggered, reattempting the task until successful completion. This architecture ensures resilience and reliability by handling potential errors proactively. Role. The langchaincohere LLM's completion with retry function is essential for reliable text generation. Using Cohere AI's LLMs, its role is to address potential errors by incorporating a retry mechanism, improving the overall reliability of the text generation process. This function empowers users to achieve consistent and successful text generation outcomes. Despite potential challenges. Advantages. Advantage 1. Enhanced reliability. Retries significantly increase the reliability of text generation tasks. By reattempting the task when errors occur, The retry mechanism enhances the overall reliability of the process, ensuring successful completion. In scenarios where network fluctuations or other temporary issues might disrupt the initial attempts, retries provide a robust solution to ensure successful text generation. Advantage 2. Improved error handling. The retry mechanism provides a robust approach to handling unexpected errors during text generation. It allows the function to gracefully handle various errors without crashing or failing abruptly. By reattempting the task, the retry mechanism ensures that the process continues smoothly, minimizing disruption to users. Challenges. Challenge 1. Network issues. Network disruptions or instability can hinder the communication between the function and the LLM, leading to errors. These disruptions can occur due to factors like temporary network outages, congested network traffic, or unstable internet connections. The retry mechanism can help mitigate these challenges by reattempting the task when network connectivity is restored. Challenge 2. Resource constraints. Limited resources or application programming interface API limitations can restrict the number of retries. For instance, a user might have a limited number of API calls available, or there might be restrictions on the frequency of retries. Understanding and managing these constraints is crucial for optimal performance and cost efficiency. LangchainCohere React Multi-hop Parsing Parse-JSONified Tool Use Generation. Definition: a method for processing JSON formatted tool use responses generated by language model chains, involving multi-hop question answering and parsing. For example, consider a scenario where an LLM chain needs to retrieve information from multiple sources to answer a complex question. The LLM could generate instructions for a tool, such as a search engine, to retrieve relevant information. The tool's response, in the form of JSON, would then need to be processed and parsed to extract the necessary data for answering the original question. This approach employs multi-hop question answering, where the LLM uses multiple steps to retrieve information, and JSON parsing to extract information from the tool responses. Components. Component 1. LangChain, an open-source framework for building applications powered by language models. LangChain provides a modular and extensible framework for building various language model-powered applications. It allows developers to easily connect different components, such as language models, tools, and data sources, to create custom workflows. Component 2. Cohere, a large language model application programming interface specializing in natural language processing tasks. Cohere provides access to a powerful language model that can be used for a wide range of NLP tasks, such as text generation, summarization, and question answering. Cohere's API allows developers to easily integrate the language model into their applications. Component 3. React, a JavaScript library for building user interfaces. React is a popular library for building dynamic and interactive web applications. It enables developers to create reusable UI components that can be easily assembled into complex interfaces. Component 4. Multi-hop question answering, a technique for finding answers to complex questions by retrieving information from multiple sources. For example, consider a question that requires information from both a Wikipedia article and a news website. Multi-hop question answering involves retrieving information from these sources, integrating the information, and then providing a comprehensive answer. This technique is often used when the answer to a question cannot be found in a single source. Component 5. Parsing, the process of analyzing a data structure, such as JSON, to extract meaningful information. Parsing involves breaking down the JSON data into its individual components and interpreting their meaning. For example, parsing a JSON response from a search engine might involve extracting the title, URL, and summary of the retrieved web pages. Component 6. JSON, a human-readable data exchange format. JSON is widely used for exchanging data between different applications and systems. Its simple and consistent structure makes it easy to parse and interpret. Component 7. Tool use generation, the ability of language models to generate instructions for tools to be used in completing a task. LLMs can generate instructions for tools such as search engines, databases, and APIs to retrieve information or perform specific actions. This enables the creation of automated workflows where LLMs can interact with external systems to complete tasks. Architecture. This approach integrates LangChain for orchestration, Cohere for multi-hop question answering, React for UI presentation, and a process for parsing JSON formatted tool use responses. LangChain acts as the central orchestrator, coordinating the different components and workflows. Cohere is used to perform multi-hop question answering, retrieving information from multiple sources. React provides the user interface for interacting with the application. Finally, the JSON parsing component processes the tool use responses to extract the necessary data. Role. This approach enables applications to leverage the power of LLMs for tool use, while effectively handling the complexity of multi-hop question answering and JSON parsing. It allows developers to build applications that can automatically interact with external systems and retrieve information from multiple sources. The approach also provides a structured and efficient way to handle JSON formatted responses from tools. Advantages. Efficiently processes tool use responses generated by LLMs. This enables applications to handle large amounts of data from various tools in a timely and efficient manner. Facilitates multi-hop question answering for complex tasks. This allows applications to answer complex questions that require information from multiple sources. Provides a clear and structured approach to parsing JSON data. This ensures that the data extracted from JSON responses is accurate and consistent. Challenges. Requires careful consideration of the structure and format of the JSON responses. The format of the JSON response must be consistent and well defined to ensure that the parsing process is successful. Managing the complexity of multi-hop reasoning can be challenging. As the number of hops increases, the complexity of the reasoning process also increases. This requires careful planning and design to ensure that the system can handle the required reasoning steps. Ensuring robust error handling for potential parsing issues. It is important to handle potential parsing errors gracefully and ensure that the application can continue operating without any unexpected issues. Advantage 1. The system can leverage the capabilities of Cohere's advanced language models for various tasks, including text generation, summarization, and question answering. One key advantage of this system is its ability to leverage the powerful capabilities of Cohere's advanced language models for various tasks, including text generation, summarization, and question answering. This allows the system to provide comprehensive and accurate responses to user queries. Advantage 2. The use of multi-hop reasoning allows the system to infer answers from multiple sources, providing more comprehensive and insightful responses. The use of multi-hop reasoning is another significant advantage of this system. It enables the system to infer answers from multiple sources, providing more comprehensive and insightful responses. This capability is particularly valuable when dealing with complex questions that require understanding relationships and drawing conclusions from multiple pieces of information. Advantage 3. The system can potentially be used for various applications including research, education, and customer service. This system has the potential to be used for various applications, including research, education, and customer service. For instance, in research, it could be used to analyze large amounts of data, including citations, and extract key insights. In education, it could be used to provide students with personalized learning experiences and answer their questions in a comprehensive and informative manner. In customer service, it could be used to automate responses to customer inquiries and provide personalized support. Challenge 1. Extracting accurate information from citations can be challenging, especially for complex or ambiguous citations. A major challenge in this system is extracting accurate information from citations, especially when dealing with complex or ambiguous citations. Citations can vary significantly in their structure and formatting, making it difficult for the system to reliably extract relevant information. Challenge 2. Multi-hop reasoning can be computationally expensive, especially for large datasets or complex queries. Another challenge is the computational expense associated with multi-hop reasoning, particularly when dealing with large datasets or complex queries. Performing multi-hop reasoning over a vast amount of information can be computationally demanding, requiring significant processing power and time. Summary of langchaincohere React multi-hop prompt render messages. NaN. Langchaincohere React multi-hop prompt render messages is a component that renders a list of messages for use in a conversation-style chatbot interface. It uses Cohere's large language model (LLM) capabilities to generate responses based on previous messages and user input. The component facilitates a natural dialogue between users and the chatbot, allowing for seamless interactions and dynamic information exchange. Component 1. Langchaincohere React multi-hop prompt, which handles the creation and execution of the multi-hop prompt. This component functions as the core of the conversational flow, enabling the user to interact with the chatbot through a series of prompts, each building upon the previous one. It utilizes Cohere's LLM to generate responses based on the prompt and historical context. For instance, if a user asks about a product, the prompt might first ask about the product category and then, based on the user's response, inquire about specific features. Component 2. Cohere's large language model (LLM), which provides the underlying language model for generating responses. Cohere's LLM acts as the brain of the chatbot, capable of understanding and generating human-like text in response to prompts and user input. It leverages advanced natural language processing techniques to analyze the context of a conversation and generate coherent and relevant responses. Component 3. Render messages component, which displays the conversation history in a user-friendly format. This component provides a visual representation of the dialogue between the user and the chatbot. It displays the conversation history in a chronological order, allowing users to easily track the flow of the conversation. The architecture consists of LangChain orchestrating the flow of information, with Cohere's LLM generating responses based on user input and conversation history. The render messages component displays the conversation. LangChain serves as the orchestrator, managing the flow of information between the different components. It receives user input, passes it to the Cohere LLM for response generation, and then utilizes the render messages component to present the conversation to the user. This seamless interaction allows for a natural and engaging chatbot experience. This component is crucial for creating a conversational user experience in chatbot applications. It allows for natural back and forth interactions between users and the chatbot. Using Cohere's LLM for intelligent response generation. The component plays a vital role in enabling chatbots to have human-like conversations, providing users with a more interactive and engaging experience. Provides a conversational interface for chatbot interactions. This component allows users to interact with chatbots in a natural and intuitive manner, mimicking real-world conversations. It enhances user engagement by providing a familiar and comfortable communication experience. Leverages Cohere's powerful large language model (LLM) capabilities for intelligent response generation. By leveraging Cohere's LLM, the component enables the chatbot to generate responses that are contextually relevant, grammatically correct, and human-like. This enhances the overall quality and accuracy of the chatbot's responses, facilitates natural language understanding and response generation. The component enables the chatbot to understand and respond to natural language input, making it more accessible and user-friendly. It eliminates the need for users to learn specific commands or syntax, allowing for a more intuitive and natural conversational experience. Handling complex multi-hop prompts and ensuring accurate response generation. Handling multi-hop prompts, which require the chatbot to follow a sequence of logical steps to arrive at a final response, can be challenging. The component must ensure that the LLM correctly understands and interprets each prompt within a sequence and generates accurate responses based on the accumulated context. Managing the state of the conversation and keeping track of previous messages. Keeping track of the conversation history and maintaining the context is crucial for generating accurate and relevant responses. The component needs to effectively manage the state of the conversation, remembering past interactions and incorporating them into future responses. Optimizing performance and scalability for large-scale chatbot deployments. Scaling the chatbot system to handle a large volume of user interactions is essential for widespread adoption. The component needs to be optimized for performance and scalability, ensuring that it can handle a high number of requests without compromising response time or accuracy. LangchainCohere React Multi-Hop Prompt Render Observations. NaN. A component within the LangChain framework designed to handle the process of rendering prompts for multi-hop question answering. Utilizing Cohere as the underlying language model. Component 1. LangChain is a powerful framework for building and deploying language model applications. It provides a modular architecture that enables users to easily connect and combine different components, such as language models, data sources, and other tools. LangChain offers functionalities for tasks like question answering, summarization, and text generation. It allows developers to build custom workflows and pipelines for diverse natural language processing applications. Component 2. Cohere is an advanced language model developed by Cohere Inc. that excels in various natural language processing tasks, including text generation, summarization, and question answering. Cohere's models are known for their ability to generate high-quality and coherent text, making them suitable for a wide range of applications. The model has been trained on massive datasets, giving it a deep understanding of human language and enabling it to generate creative and informative outputs. This component relies on LangChain to manage the intricate process of prompt engineering for multi-hop question answering. LangChain facilitates the organization of the multi-hop reasoning process, allowing for the sequential retrieval and processing of information. Cohere plays the role of the language model, responsible for generating responses based on the constructed prompts and the provided context. This component acts as a bridge, enabling seamless communication between LangChain and Cohere for the purpose of question answering. Its primary function is to facilitate the flow of information between the two components, allowing LangChain to manage the prompt construction process and enabling Cohere to deliver accurate and contextually relevant responses. This interaction facilitates complex multi-hop reasoning, where the model needs to access and process information from multiple sources to arrive at a correct answer. The component leverages the advanced capabilities of Cohere's language models, enabling it to generate highly sophisticated and contextually relevant responses to user queries. Cohere's models are capable of understanding the nuances of language and generating outputs that are not only grammatically correct but also semantically meaningful. This makes the component ideal for applications that require complex reasoning and deep language understanding. The component simplifies the process of prompt engineering for multi-hop question answering. It provides a user-friendly interface for constructing prompts that incorporate multiple sources of information and allow for the retrieval of relevant data from different locations. This simplifies the development process and allows developers to focus on the core logic of their applications rather than spending time on intricate prompt engineering tasks. Ensuring the coherence of multi-hop reasoning remains a significant challenge, as the complexity of the question increases and the reasoning process involves accessing multiple sources of information. Ensuring that the model's responses are logically consistent and free from contradictions becomes crucial. Maintaining a coherent chain of reasoning across multiple hops requires careful prompt design and effective model training. Handling complex question structures presents another challenge. Multi-hop questions often exhibit intricate syntax and semantics, requiring the model to decipher the user's intent and extract the necessary information for accurate answering. The component needs to be able to handle a wide range of question structures, including those with nested clauses, conjunctions, and other complex linguistic features. LangchainCohere React Multi-Hop Parsing Parse-JSONified Tool Use Generation. Definition. This variable represents a comprehensive approach that leverages LangchainCohere and React to facilitate multi-hop question answering through parsing JSONified tool usage generation. Components. Component 1. LangChain is a framework for building and deploying large language model LLM-powered applications. It offers a wide range of tools and libraries to streamline the development of AI-driven applications. For instance, LangChain can be used to build conversational AI chatbots, automate document summarization, or create custom search engines. Component 2. Cohere is a natural language processing (NLP) application programming interface API for generating text, summarizing, and more. It enables developers to integrate advanced NLP capabilities into their applications. For example, Cohere can be used to generate creative content, translate languages, or analyze sentiment in text. Component 3. React is a JavaScript library for building user interfaces. It enables developers to create dynamic and interactive web applications with a focus on user experience. For example, React can be used to create complex dashboard interfaces, interactive maps, or e-commerce platforms. Component 4. Multi-hop question answering is the process of retrieving answers to questions that require multiple steps of reasoning. It involves understanding the context of the question, identifying relevant information sources, and combining information from different sources to arrive at a final answer. For example, a multi-hop question might require the system to first find a relevant document, then extract specific information from that document, and finally combine that information with other data to answer the question. Component 5. JSON-ified tool usage generation is the process of generating JSON-formatted instructions for tools. These instructions specify the actions that the tool should perform and the data that it should use. For example, a JSON instruction might tell a tool to extract specific information from a website, process that information, and then return the results in a particular format. Architecture. The architecture incorporates LangChain's capabilities to orchestrate interactions between Cohere, React, and external tools. Cohere generates responses based on input prompts, which are then parsed and translated into JSON instructions for tools. These tools can then be utilized to retrieve specific information or perform actions based on provided instructions. The results are then presented to the user through a React-powered user interface. Role. This variable plays a pivotal role in enabling seamless, multi-hop question answering by streamlining the process of generating and executing tool instructions. It acts as a central hub for coordinating the different components involved in question answering process. This allows developers to focus on building custom logic and user interfaces while leveraging power of LangChain, Cohere, and React to handle the complex underlying operations. Advantages. Enhanced accuracy utilizing multiple steps of reasoning to improve answer precision. By breaking down complex questions into smaller steps, the system can better understand the context and provide more accurate answers. This is especially important for questions that require specialized knowledge or understanding of multiple concepts. Increased flexibility, ability to integrate various external tools for specific tasks. The system can leverage a wide range of tools to handle different types of questions and information retrieval needs. This flexibility allows developers to tailor the system to specific domains and use cases. User-friendly interface leveraging React to create an intuitive user experience. The user interface provides a simple and easy-to-use way for users to interact with the system. This user-centric approach ensures that the system is accessible to a wide range of users, regardless of their technical expertise. Challenges. Complex system design coordination between multiple components requires careful architecture. The system involves multiple components working together, which requires careful design and implementation to ensure smooth communication and efficient operation. Robust error handling ensuring proper error management for potential issues during tool execution. The system needs to be able to handle errors that may occur during tool execution, such as invalid input, tool failures, or unexpected data formats. Performance optimization balancing the complexity of multi-hop reasoning with efficient response time. The system must be able to handle complex reasoning tasks while providing fast and responsive results. This requires careful optimization of the code and algorithms to minimize processing time and ensure a smooth user experience. One of the primary challenges faced by the parse actions function is the complexity of accurately identifying and classifying actions from diverse user inputs, especially when dealing with ambiguous or nuanced language. This complexity arises from the inherent ambiguity of natural language, where the same words or phrases can have different meanings depending on context. For example, the phrase play music could refer to playing music on a specific device, searching for a specific song, or generating music. Accurately interpreting the intended action requires sophisticated language processing capabilities and the ability to handle context and ambiguity effectively. The potential for errors in action interpretation leading to incorrect or unexpected execution. Results. Another challenge associated with the pass actions function is the potential for errors in action interpretation, which could lead to incorrect or unexpected execution results. If the function misinterprets the user's intent or fails to extract the necessary information, the framework may execute the wrong action or provide an irrelevant response. For example, if a user asks what is the capital of France, but the pass actions function interprets the action as find the population, the framework will provide the population of France rather than its capital. Ensuring accurate interpretation is crucial for maintaining the framework's reliability and providing users with a seamless experience. LangchainCohere React Multi-Hop Prompt Render Structured Preamble. NaN. A feature that allows you to create structured prompts for multi-hop reasoning tasks using Cohere. This feature assists with the creation of prompts that are better organized, simpler to understand, and more suitable for multi-hop question answering. For example, imagine asking a question that requires multiple steps to answer what is the capital of the country, where the Amazon River originates. With structured prompts, you can break down this question into smaller, more manageable steps, making it easier for the language model to process and understand. Component 1. Cohere Application Programming Interface for Large Language Models, which is a set of tools that enables interaction with Cohere's powerful language models. These models excel at understanding and generating human-like text, making them ideal for tasks like question answering and text summarization. Component 2. LangChain for Chain Composition, a library designed to build and manage complex chains of tasks involving language models. It provides a flexible framework for connecting different components, such as prompts, language models, and data sources, into cohesive workflows. LangChain makes it easy to create and configure sophisticated multi-hop reasoning systems. Component 3. React for User Interface Development, a popular JavaScript library for building dynamic and interactive user interfaces. React makes it easy to create intuitive and responsive web applications, providing a framework for structuring the front end of the multi-hop question answering system. This allows users to interact with the system, input questions, and receive clear and detailed answers. The architecture involves using LangChain to create multi-hop reasoning chains that incorporate Cohere's language models and a React user interface for user interaction. This architecture allows for a seamless workflow where users can input their questions, and LangChain manages the process of breaking down the question into smaller steps, executing those steps using Cohere's language models, and presenting the results in a user-friendly manner. This feature makes it simpler to build and use multi-hop question answering systems, which are important for tackling complex tasks. Multi-hop question answering involves understanding and answering questions that require reasoning over multiple pieces of information. This is particularly valuable in domains like research, knowledge management, and customer service, where answers often require accessing and integrating information from various sources. Structured prompt creation allows for breaking down complex questions into smaller, more manageable components. This makes it easier for the language model to understand the intent of the question and arrive at a more accurate answer. Simplified chain creation empowers users to easily assemble and configure the necessary components for their multi-hop reasoning tasks. This streamlines the process of building question-answering systems, allowing developers to focus on the core logic of their applications. User-friendly user interface provides a clear and intuitive way for users to interact with the multi-hop question answering system. This makes it accessible to a broader audience, even those with limited technical experience. Handling complex multi-hop reasoning requires careful design and implementation to ensure that the system can effectively navigate multiple steps and integrate diverse sources of information. This is particularly challenging when dealing with complex questions that involve multiple levels of reasoning and require sophisticated logic. Maintaining coherence between prompts and responses is crucial for ensuring that the system generates consistent and meaningful answers. This requires careful consideration of the language model's capabilities, the structure of the prompts, and the way in which the information is presented to the user. This is especially important for multi-hop reasoning, where the user may need to follow the chain of reasoning to understand the final answer. LangChain-Cohere React Multi-Hop Parsing Cohere Tools React Agent Output Parser. NaN. The Cohere Tools React Agent Output Parser is a LangChain component designed to extract valuable information from the output of a Cohere React agent. The agent's response, often a complex JSON object, can be difficult to decipher. This parser simplifies this process, making the information easier to understand and use. Component 1. The Cohere React agent is a powerful tool that uses natural language processing to generate responses to prompts. It can be used for a wide variety of tasks, including question answering, text summarization, and code generation. Component 2. LangChain is an open-source framework that provides tools for building and deploying language models. It offers a variety of components for tasks such as data retrieval, text processing, and model execution. LangChain's modular design makes it easy to combine different components to create custom applications. The parser relies on LangChain's strengths in handling structured data. It uses a predefined schema to map the relevant fields from the Cohere React agent output. This schema outlines the expected structure of the response, allowing the parser to pinpoint and extract specific data points with accuracy. The Cohere Tools React Agent Output Parser acts as a bridge between the complex output format of the Cohere React agent and the simpler, more manageable data structures that LangChain can process. By doing so, it enables seamless integration of the Cohere React agent with other LangChain components. This is crucial for building applications that leverage the power of both technologies. Advantage 1. The parser significantly simplifies the process of extracting data from the Cohere React agent's output, making it much easier for developers to work with. Advantage 2. By providing a standardized way to access the data from the Cohere React agent, the parser enhances data utilization. This allows developers to seamlessly integrate the information into their applications, improving efficiency and functionality. Challenge 1. The output from the Cohere React agent can be complex, often requiring intricate parsing logic to extract the desired data. This presents a challenge for the parser, which needs to be flexible enough to handle various output formats. Challenge 2. The Cohere React agent is a constantly evolving technology, with updates and changes to its output format. The parser needs to maintain compatibility with these updates to ensure its functionality remains reliable. This requires careful monitoring and adjustments to the parsing logic. LangChain-Cohere React Multi-Hop Prompt Render Role Summary. NaN. The LangChain-Cohere React Multi-Hop Prompt Render Role is a specialized component designed to Generate multi-hop prompts for question answering. Leveraging the capabilities of the Cohere language model. This role is crucial for effectively utilizing Cohere's power in scenarios requiring multiple reasoning steps to arrive at a comprehensive answer. Component 1. LangChain serves as the orchestrator in this system, seamlessly managing the communication flow between various components. It facilitates the interaction between the prompt, the Cohere large language model (LLM), and the application itself. LangChain acts as a bridge, ensuring a smooth exchange of information and enabling a coordinated workflow. Component 2. Cohere is a powerful large language model (LLM) that plays a vital role in the process by generating responses to multi-hop questions. It excels at handling complex queries that necessitate multiple steps of reasoning and information retrieval. For instance, a multi-hop question could involve asking for the capital city of a country, and then, based on that information, requesting the population of that capital city. Component 3. The React multi-hop prompt component is responsible for crafting prompts that are carefully designed to guide the LLM through a sequence of steps, ultimately leading to a comprehensive answer. This component takes a multi-hop question and breaks it down into smaller, manageable parts, ensuring that the LLM can process each step individually and efficiently. The architecture of this system is built upon the foundation of LangChain, which orchestrates the flow of information between the key components. The React multi-hop prompt component is responsible for generating the multi-hop prompt structure, which serves as a roadmap for the Cohere LLM to follow. The Cohere LLM then processes each step of the prompt, eventually arriving at the final answer. The application interacts with the entire system, receiving the final answer and potentially providing additional context or instructions. The render role plays a crucial part in facilitating effective multi-hop question answering. It focuses on generating a well-structured multi-hop prompt that acts as a guide for the Cohere LLM. This role strategically breaks down a complex question into smaller, manageable steps, making it easier for the Cohere LLM to reason and retrieve information sequentially. Multi-hop prompts significantly enhance the accuracy of question answering by allowing the LLM to focus on smaller, more manageable parts of the question. This approach reduces the risk of errors that can occur when dealing with complex queries directly. For example, instead of trying to answer a question about the population of a city, the LLM can be prompted to first identify the country the city belongs to, then determine the population of that country's capital city, and finally, using the provided information, derive the estimated population of the target city. Multi-hop prompts facilitate a deeper understanding of complex questions by breaking them down into smaller, more digestible chunks. This process allows the LLM to process each step individually, leading to a more comprehensive and nuanced understanding of the entire question. This is particularly helpful when dealing with questions that require multiple layers of reasoning and information retrieval, such as understanding a complex historical event or analyzing a scientific theory. Crafting effective multi-hop prompts can be a challenging task that requires careful consideration of the question structure and the capabilities of the underlying large language model (LLM). The process involves understanding the nuances of the question, identifying the key reasoning steps, and structuring the prompt in a way that guides the LLM through each step successfully. The success of multi-hop prompting heavily relies on the capabilities of the underlying large language model (LLM). While LLMs have made significant progress, they still face limitations in handling complex reasoning or knowledge retrieval. It's crucial to choose an LLM that is well suited for the specific task at hand, and to carefully consider its limitations when designing the multi-hop prompts. This includes understanding the LLM's knowledge base, its reasoning abilities, and its potential biases, ensuring that the prompts are tailored to its capabilities and address any potential challenges. LangchainCohere React Multi-Hop Prompt Render Structured Preamble. Definition. A structured preamble is a technique used in natural language processing (NLP) to furnish context to a language model regarding the task at hand. This approach is especially valuable in multi-hop question answering, where the language model requires access to multiple data sources to formulate an answer. Components. Component 1. A sequence of actions or steps that are essential for the completion of the task. For instance, in a question answering system, the steps could be read the document, extract relevant information, and formulate an answer. Component 2. A collection of pertinent facts or background information that helps the language model comprehend the context of the question. This could involve details such as the time period, location, or specific entities related to the question. For example, in a question about a historical event, the preamble might include the date, location, and key participants involved in the event. Component 3. A list of potential sources of information that the language model can refer to. This could be a set of documents, websites, or databases that contain relevant information to answer the question. For example, in a question about a scientific topic, the preamble could include links to relevant scientific publications or online repositories. Architecture. The structured preamble is integrated into the prompt presented to the language model. The language model subsequently leverages the information within the preamble to generate a more precise and pertinent response. For instance, if the preamble specifies the relevant documents and provides context, the language model can focus its attention on those sources and extract relevant information to construct a more accurate answer. Role. The structured preamble serves as a crucial guide for the language model, steering it towards the correct answer. By providing context and outlining the steps involved, it enhances the model's ability to understand the task and deliver an appropriate response. For example, in a question about a specific topic, the preamble can help the model avoid generating irrelevant responses by explicitly specifying the scope of the question and the relevant sources of information. Advantages. The structured preamble contributes to the enhanced accuracy and relevance of the answer generated by the language model. By providing context and guidance, it allows the model to focus its attention on the relevant aspects of the task, resulting in a more accurate and focused response. For instance, in a question about a specific event, the preamble can provide historical background and context, allowing the model to generate an answer that is more informed and relevant to the question. The structured preamble can significantly improve the efficiency of the language model. By providing a clear understanding of the task and relevant information, it allows the model to process information more effectively and avoid unnecessary processing steps, resulting in faster response times. For example, by specifying the relevant documents and keywords, the preamble can help the model quickly identify the relevant information without having to process irrelevant data. Challenges. Crafting a comprehensive and informative preamble can be a challenging task. It requires a deep understanding of the task, relevant information, and potential sources of information. For instance, creating a preamble for a complex question involving multiple sources of information can require Extensive research and careful selection of information to ensure that the preamble is comprehensive and relevant. Ensuring that the preamble is concise and readily understandable is crucial. A verbose or overly complex preamble can overwhelm the language model and hinder its ability to process the information effectively. For instance, in a question about a specific topic, the preamble should provide only essential context and relevant information without including extraneous details that may confuse the model. Langchaincohere rank. A YAML document outlining the capabilities and characteristics of langchaincohere rank. Langchaincohere rank utilizes Cohere's advanced ranking application programming interface API to enhance the precision of retrieved documents by prioritizing the most relevant ones based on their context and content. This process ensures that users receive the most pertinent information, leading to a more efficient and effective search experience. Component 1. Cohere Ranking API is a powerful tool offered by Cohere that enables developers to rank and order a list of documents based on their relevance to a given query. This ranking system leverages advanced natural language processing (NLP) algorithms to analyze the content and context of documents, producing a ranked list that reflects their relative importance to the query. Component 2. LangChain is an open-source framework that simplifies the development and integration of various language models, including Cohere's ranking API. LangChain provides a flexible and modular architecture that allows developers to easily connect and orchestrate different components, creating powerful and customized applications for tasks like document retrieval and ranking. LangchainCohere rank seamlessly integrates with the LangChain framework, leveraging its capabilities to connect with and utilize Cohere's ranking API. This integration enables LangChain applications to enhance their document retrieval capabilities by incorporating Cohere's sophisticated ranking algorithms, thereby improving the overall accuracy and relevance of search results. LangchainCohere rank plays a crucial role in optimizing document retrieval by refining the relevance of retrieved documents through the use of Cohere's ranking capabilities. By leveraging Cohere's ranking API, LangchainCohere rank ensures that the most relevant documents are presented first, providing users with a more targeted and efficient search experience. This enhanced relevance leads to improved search accuracy and a better understanding of the information being retrieved. By utilizing Cohere's ranking capabilities, LangchainCohere rank significantly improves the relevance of retrieved documents, ensuring that users receive the most pertinent information related to their search query. This enhancement in relevance leads to a more focused and accurate search experience, as users are presented with documents that directly address their needs. The integration of Cohere's ranking API within LangchainCohere rank results in enhanced search accuracy. Cohere's advanced ranking algorithms provide a more precise and nuanced understanding of document relevance, leading to more accurate search results that align closely with the user's intent. This improved accuracy allows users to efficiently find the information they require, saving time and effort. While Cohere's ranking model offers significant advantages, it is essential to acknowledge the potential for bias in the ranking process. Like any AI-powered system, Cohere's ranking model can inherit biases present in the data it is trained on, potentially leading to skewed or inaccurate ranking results. It is crucial to be aware of this potential bias and to implement strategies to mitigate its impact, ensuring fair and unbiased search results. The use of Cohere's API comes with an associated cost, as Cohere charges for API calls based on usage. This cost can be a factor to consider when integrating Cohere's ranking capabilities into applications, as it requires careful planning and resource allocation to ensure sustainable and cost-effective use of the API. LangChainCohere React Multi-Hop Parsing Parse Actions Summary. A description of the function and its role in the LangChain ecosystem. Parse actions is a core function within LangChain's Cohere React multi-hop parsing module. This function takes a raw, structured response from the Cohere application programming interface API and converts it into a format suitable for LangChain's chain architecture. Component 1. Cohere API response. The input to parse actions is the raw output of the Cohere application programming interface API. A JSON-like structure containing multiple sections. Component 2. LangChain Action Dictionary. The output of parse actions is a dictionary where each key represents a step or action in the multi-hop reasoning process, and the value is another dictionary containing information about that action. LangChain's multi-hop reasoning architecture is built on the premise of breaking down complex queries into a series of individual steps or actions. Each action is represented by a LangChain component, and the overall process is managed by LangChain's chain infrastructure. Parse actions plays a crucial role in bridging the gap between Cohere's application programming interface API response and LangChain's action-based architecture. This enables efficient utilization of the reasoning capabilities within LangChain. Advantage 1. Enables seamless integration with LangChain's chain architecture. For example, it enables the integration of multiple components of LangChain architecture and allows for efficient processing of multi-step reasoning tasks. Advantage 2. Simplifies the handling of multi-hop reasoning steps. A real-world example is in question answering, where a complex question might require several steps to find the right answer. Challenge 1. Handling complex Cohere responses. This may involve dealing with responses that contain multiple sections, nested structures, and different data types, especially when handling responses from advanced Cohere models. Challenge 2. Ensuring consistent action representation across different Cohere models. For example, different Cohere models may provide responses in different formats or with varying levels of detail, which can pose a challenge to maintaining a consistent action representation for integration with LangChain's chain architecture.